are going to invite our next speaker for session number 1 on climate and environmental impacts of natural and halogenated refrigerants in chillers and condensing units. Welcome, Dr. David Behringer from Öko-Recherche. Hello.
Can you hear me?
Perfectly fine.
Okay. How do I get to the slides? Because taking over is not an option. But,
Okay, we will work on that in 1 minute. Let me just tell our participants who you are, right? So you are a scientific consultant at Öko-Recherche, which is an independent environmental research institution and consultancy based in Frankfurt, Germany. And today, David Behringer is going to talk about a study on climate and environmental impact of natural and halogenated refrigerants in chillers and condensing unit that Öko-Recherche conducted for the German Environment Agency. And it's so great to have you here with us, David. But before you start, let me quickly tell the participants how we are going to work in our Q&A session. So, dear participants, you can either leave your questions in the chat or raise your hand, okay? For raising your hand, just click on the hand icon, and then I will see you and I will get to you after the presentation, and you have the opportunity to ask your question directly. Until then, your microphone stays muted, and once I call your name, we will give you the permission to unmute yourself, okay? And then you can speak and we can hear you. The questions must be asked in English, since we only have one-way interpretation. For the questions in the chat, you can write them in French, Spanish, or English, and they will be translated from our team. And I would kindly ask you to highlight or vote the question in the chat that most interests you by giving it a thumb up, okay? So this way, in the end, our team can figure out which question I should ask, okay? And please, when writing a question in the chat, make sure that it's short, not more than 200 characters. All right, and with that said, Daniel, the floor is yours. David, sorry, the floor is yours.
No problem, thank you. Yeah, hello. My name is David Behringer. I'm from the Öko-Recherche, and I wanted to present to you the results from a study we conducted for the German Environment Agency, the Umweltbundesamt, with this very verbose title. I'm not going to repeat it. It's the study will be in German, but there's a English summary, and there will be a peer-reviewed English paper based on this data. So I think it should be available for everyone. So why did we want to do this, and how did we do it? The idea was to assess the direct and indirect emissions of different refrigerants with the GWP below 750 in chillers and condensing units. So the background was a bit that there's often the criticism that the direct emissions of the refrigerant alone are not the relevant thing, and there should be an assessment of both direct and indirect emissions. And then also there's often a criticism attached that certain refrigerants would then fare worse. And we wanted to look into this and see how the situation currently is, specifically for refrigerants with a GWP below 750, because the higher GWP refrigerants will either way leave the market due to HFC phase down, etc., and bans. So we looked at different refrigerant types. For one, the HFCs and mixtures of saturated and unsaturated HFCs. These are just the standard HFCs and mixtures we all know. And then the purely unsaturated HFCs and HCFCs. We call them UHCFCs or HFCs, but they're more commonly referred to as HFOs or HCFOs. And then, of course, the natural refrigerants. We opted for an approach that is more quantitative. So we didn't want to just directly compare two systems with different refrigerants and then make a judgment based on that, because there's always the problem that, yeah, okay, you pick this one system and one other system, and the conditions are definitely not identical, and are the systems with the same age, stuff like that. So we thought a bit of more quantitative approach would be better. So we looked at the technical data sheets, because there should be the data available under comparable conditions, because the eco-design regulations dictate certain conditions under which then values for cooling capacity, cooling capacity and energy demand would be available. We did this, wasn't as easy as it sounds, and so we sampled always the smallest and largest systems of each product line per manufacturer. The reasoning is that a lot of manufacturers per product line give a data sheet, and then there are systems from a certain minimum capacity to a maximum capacity. And I looked at those in detail, and they scale extremely linearly. So it is basically enough to just sample the smallest and the largest system. So that's what we did. For this, then we collected 81 air-cooled chillers, 46 water-cooled chillers, and 29 condensing units. These numbers are only referred to specific operating temperatures. So for the chillers, it was high or low, depending on process of comfort, cooling, and medium temperatures for condensing units. We gathered more data, but there was just not enough fully available data to compare other temperature types. So the following information will be for these operating temperatures. And the metric that we looked at, and that's also where we needed all the information, was the total equivalent warming impact. So this is what we wanted to calculate, and this is basically what it is. Looks very big now, but it's just simply the direct emissions plus the indirect emissions. And the direct emissions are just it's just what emits, the amount of refrigerant that emits from a system over the lifetime and at end of life. So these entire emissions are summed up basically, and then multiplied with the GWP to get a value in CO2 equivalents. And then you add to that the indirect emissions, which are the emissions from the electrical energy generation to power the compressor, basically. So, and this also over the entire lifetime. And with this, you get the TEV, which is not really the total warming impact, because some sources are missing. We looked into this then later also for the paper, but they capture, the TEV captures a lot. So that's why we opted for it. The data that we gathered is it was based on the technical data sheet information and some published information, but then also certain assumptions. So you can later go through this and look at the assumption in detail. They're also in the report, but you might come to the conclusion I would have picked a different value. That's totally fair. And that's also why I did some simulations and looked into the impact of these assumptions that we made to see would that change the result. And just to jump ahead a bit. So for the current CO2 emissions per kilowatt hour electrical energy, the TEV is mainly driven by the indirect emissions. So the blue part above. So you can say that the efficiency is currently the relevant parameter. Efficiency, because this is basically what you calculate there. It's the how much cooling capacity do I get per kilowatt hour electrical energy. And just that worked. Just to very quickly give a very brief look into this these simulations that I did. I looked here at the HFCs and mixtures. Because I was interested in the share of the direct TEV. So if I jump back, the blue part of the total. So this is what you see on the y-axis always. And why not? I also did it for the HFOs and the natural refrigerants, but there obviously the direct portion is very small due to the very low GWP. So in the left figure, you see basically all the values that the operating time can take. So it's from 0 to 100%, doesn't run at all, or runs constantly. So because we had to pick a certain operating times, and so you see what happens if I vary the operating time, and you can mainly look at the mean not dashed lines, and there you can see that already from 10% of an entire year in terms of operating time, the share of the direct TV drops below 10%. So it's under the current CO2 equivalence for the energy generation. So it's it doesn't have a significant impact on our results. And to the right, you see for sampled 4 operating times, and then I just varied the basically greenness of the electrical energy. So if you go on the x-axis from left to right, the energy gets greener. So electricity has less climate impact. And then the dashed line you see is the current situation. So here you also see that it takes a long time for the electricity to get very green to have an impact here. Okay, so with this we can look at the results. And what I did here is to have some measure of comparing the TVs for the different systems with very different sizes, which obviously impacts the TV itself. I divided the TV by the cooling capacity per system. So you see the dots, those are all the individual units, the colors are the refrigerants, and then the size of the dot is the cooling capacity. And then I grouped them according to these refrigerant types that I outlined before, and then the type of system here, the chillers, so air-cooled and water-cooled chillers. And then you can see, you can get a better picture of directly comparing the systems. And for air-cooled chillers, we see a very large overlap. So there might be some, I mean, obviously someone has the highest median. In this case, it's the HFCs and mixtures, but it doesn't really mean much because there's so much overlap. We also see that the ZE systems have the largest spread from like basically most efficient or least TV per kilowatt to highest. So this very large spread. And propane also has a broad range. And generally, you can say that the ammonia chillers tend to be more efficient, just on average, because they also have some of the lowest TVs. For the water-cooled chillers, it's again a lot of overlap between the data. Unfortunately, we had very little data for 1233 ZD, just 2 data points, and also very little data for propane. But from what we can gather here, we see that the ZD and the ammonia systems have the lowest TVs per kilowatt, and this one ammonia system had very small ammonia system had the highest TB, though they're also very efficient, can be very efficient. And you can also see that propane was only present in very small systems. So you basically have to compare it more to the very small systems for the HFCs and mixtures. So it's rather comparable. And for the condensing units, the same figure again. Again, also a lot of overlap. We have relatively comparable results between the refrigerants, and in this case now the naturals have slightly, so the highest median as had the HFCs and mixtures before, again doesn't mean much because the overlap is so big. We have some units with HFCs and mixtures who had the lowest TV per kilowatt, and this is mainly R450A, though there are only 2 data points. And for 513A, we had a very mixed bag like ZE before. It's very efficient or not so efficient. For YF, there were only 2 data points, so it's bit hard to draw conclusions from that. And the natural refrigerants also had very comparable results. And again, in this case, it's the CO2 that has this very broad distribution compared a bit to the ZE before. So you can also say that the result is here rather comparable if you look at the TEVI. But since the TEVI is not, so the only parameter when you look at emissions of refrigerants, we also looked at the atmospheric degradation products. So what happens to the refrigerant once it emits to the atmosphere? And generally for the fluorinated refrigerants, we can say that some purely degrade to HF, hydrofluoric acid, and CO2. So for example, HFC 32 just fully degrades to HF and CO2, but we have some fluorinated gases that degrade fully to TFA. It was mentioned before, the 1234YF only has one degradation product, that is TFA, which is quite problematic. And then we have, again, others that are very complex. So that's why I put a picture in there for 1234ZE as an example, because some of them can basically degrade to a lot of things. So mainly they will degrade to HF and CO2, to be honest. But there is the possibility for pathways depending on the degradation route, so that either TFA or HFC23 can be created. So the HFC23 pathway is rather new, newly discovered. The TFA pathway has been known before. There are also different ways that can lead to TFA and also HFC23, which has a very high GWP. So this introduces a new problem, because then you wouldn't necessarily say that the HFO itself, or in this case the UHFC 1234ZE, has a very low GWP. If you add to it the potential of HFC23 creation, one recent study estimated it to be the total GWP to be 20. So in all honesty, if you do this and you take the, in this case it's also called the direct and indirect emission, which is a bit confusing because it means something different here. So just the direct GWP and also the GWP of the degradation products. If you combine those, like in the 20 here, you should do the same for also for the naturals. So I think propane would then have a GWP of 9.5 or 9 or something. But yes, but generally the natural refrigerants, they have no high GWP degradation products like HFC23 or something, and no PFAS degradation products, because they're not fluorinated, they can create those. So what we did is we also calculated the TFA potential directly. Just calculated how much TFA could be created from the emissions of the systems that we looked at, and you see that natural refrigerants and HFC 32 have no TFA potential, whereas refrigerants with YF have the highest TFA potential. That's why all these mixtures have built up TFA, because they have high YF content. And you see to the left, that's the absolute value. So the chillers obviously have the highest contribution, absolute contribution, due to very large charge sizes. And to the right, you can see that the condensing units per kilowatt cooling capacity have the highest contribution, but absolutely it's much lower. And if you're wondering why the YF is lower than the mixtures with YF, that's just the charge size. So it's just much lower for these YF systems. So that's why the TFA is lower. So finally, this is a bit of an overview of the climate and environmental impacts of the analyzed units. So the systems that we looked at, there you can say that regarding the refrigerant type, the TEVI is comparable. We've seen that there's not really a significant difference in that variable, but the GWP is obviously different. So the HFCs and mixtures have rather high GWPs, and the unsaturated fluorinated ones much lower, and the natural refrigerants even lower. And the HFC23 pollution potential is present in some of the HFCs and mixtures. Most of the unsaturated ones, actually only the YF does not have that potential, and is not present in natural refrigerants. For TFA, it's comparable again. The HFCs and mixtures, almost all of them have TFA potential. The exception here would be the HFC32. All of the unsaturated HFCs and HTFCs can create TFA, and again, none of the natural refrigerants can do that. So, if you look at this for the systems we analyzed, the result should be that natural refrigerants should be the preferred choice in chillers and condensing units whenever possible, because they do not come with this climate or environmental impact. I think that's it from my side. And yeah, if you have any questions, you can ask them. And thank you for the attention.
Thank you so much, David Behringer. And yes, people are making use of clapping hands. Thank you very much for conducting that study and for your insightful presentation. And yes, dear participants, now is your time to ask a question directly to David Behringer. You can either use the chat or click on the hand button. I'm going to show it right now, right? And then I can see who has a question for you. Let's see. Wait for some seconds. Wait, okay. Perfect. Okay, nobody wants to break the ice, is that correct? And ask a question directly. I know that you... Yes.
Yeah, here's Felix Law speaking. Felix Law from Dyken Chemical. And David, you mentioned that TeV is insignificant when you compare the different refrigerants. Would it make sense then go back to R32 and using, because TeV has not that impact, so it wouldn't make sense to return to R32 and because it's has a better safety, or it's less flammable than propane, for example.
Yeah, so it's not the TeV, it's the direct part of the TeV. Oh, now I hear myself again.
The TeV combines direct and indirect. So if we consider TeV and say, okay, TeV doesn't matter anymore, so then we can go back to then GWP should also have no influence anymore. Or is this wrong, this assumption?
No, I think there's a misconception here. So the TeV itself is basically the energy efficiency. If you, sorry, someone has his microphone on and the speakers, and okay, thank you. Sorry. So so the TeV itself, it's my point was not that the TeV is not usable or whatever. It's just the direct and indirect emissions together make up the TeV. So if you say that, if you look at the current in Germany, different than other countries, but in Germany, where you have a lot of CO2 equivalents attached to the electrical energy generation, in this case, it's the direct contribution is just it's dwarfed by the indirect contribution, but the indirect contribution is still there. And it's still there also for the HFC32 systems. They have the same. It's the same problem. That doesn't solve the problem. They still consume energy. So what we looked at is, does it have an impact? And based on our analysis for the systems that we looked at, it does not really have an impact. So if you then say this means I should use HFC32, I don't understand why you would come to that conclusion, because in the end you would say, okay, which is more efficient? Then you say both are equally efficient. Then this is the point where this factor is not that relevant. And then you go, are there further problems? And if you say flammability is an issue, to be honest, for propane, it isn't that much of an issue, flammability.
Thank
Okay.
you. Yes.
Okay.
Thank you
Yeah,
very much, Felix Flo. We have the possibility to join
Okay, maybe we
the
can do this.
networking break to go further into discussion. And David Behringer is going to be present during the networking break, hopefully, right? Yes. So for more in-depth discussion, please join the networking break session. And thank you very much, Felix Flo, for your question. We have another question coming from Benedict Mutoka. The floor is yours, Benedict. Benedict Mutoka, I think you can unmute yourself right now if you want to raise a question. Otherwise, I would give the floor to Colin Botsfeld, and then maybe we can come back to you, Benedict, in a second. Colin, can you unmute yourself?
Yes, can you hear me?
Yes, we do.
Well, thank you very much for the presentation. I raised the question why you still have TeV values in the graphs, but now I heard in the answer that actually it's because you have taken the CO2 intensity of the German electricity grid. Would it not be beneficial to have also a graph with, say, a future electricity grid, because we know where it needs to go? And then you would probably see very significantly that natural refrigerants are the choice to make.
That was in one of the figures. Sorry if that wasn't clear. It was the right figure with the TeV simulation, the right figure. That's what you wanted. It's where you go to the right on the x-axis, it gets greener. So if you're around 50 to 100 grams CO2 equivalents per kilowatt hour electrical energy, there it goes really up. And then eventually it turns to 100. I mean, at some point, it just reverses. The current situation reverses. So the indirect emissions will be irrelevant, and the direct emissions will be the only relevant part. So the thing is just that, to be honest, this will happen anyways, because the GWP of the refrigerants based on the F-gas regulation, there is no quota for the future. Also, HFC 32 has to go. It's a transitional fluid if you look at the F-gas regulation. So there is there's a path out of the HFCs. So in this case, I think it will happen sooner before the electricity is that green. Is what I'm saying. But it will be then relevant for other refrigerants with very low GWPs.
All right, thank you, Colin. Let us take a look at the chat if the team already picked a question. And please, participants, remember, if you highlight a question, if you put a thumb up to one of the questions, it will get more points and be ranked higher. So the chance of us answering to that question is higher. All right, then yes, David. You can, I mean, if you want to reply to any of the questions in the chat, feel free to choose. Yes.
I saw one where they asked about the manufacturing emissions, why they're not included. That's, I think, is a good question. It's extremely hard to get this information, but I did it. It's not in here because it's not in the report, but it will be in the paper. Production emissions will be in as a manufacturing of the refrigerant. Only the refrigerant. I don't have it's not a life cycle analysis, because to do a life cycle analysis would be perfect, but for all the systems would be possible, at least for me to do. But I think that's a good question. There was one asking about TeV that has 2 thumbs up, so I'm going to TeV be modified to include the TFA, etc. I was thinking about that, to be honest. There are, I'm not the first one who noticed that the TeV is not the total. That's would be a bit, obviously that has been mentioned before in the literature. I think Armin Hafner mentioned this in the 90s already, that it's not the, that there could be done more to include more. I tried to do this for the paper. I included more parameters. including the TFA, I think is problematic, because what would be the metric? The metric, how do you translate this to CO2 equivalents? The TEVI is a measure for the climate impact, so we have the same problem that we have with the F-gas regulation and the REACH proposal. It's just separate things. They're two separate things. That's what I tried to highlight in the last slide, that the F-gases do not only come with this one problem of climate impact, but some of them don't really have that much of a climate impact. But then they introduce just another problem, just another type of pollution. And this is, I think, we should not try to squeeze it in one metric. That's what I'm saying, but just look at it separately.
Yes, thank you very much. I would like to allow one more question, since we are already on our official break time. And I'm taking a look at the chat and I see your thumbs up, which was really nice. Just waiting for the team to select a question and forward it. And maybe while we're waiting, we try to ask Benedict again. Benedict Mutoka, are you with us? Do you want to place your question? Seems that there are some issues. All right. Okay. David, do you want to choose one last question? I saw one question coming from Philip Denzinger with 3 thumbs up, which is, please please confirm that HFC 23 is also used during production of HFCs and HFOs, and production is also very energy intensive. HFC 23 has the longest atmospheric lifetime, 228 years, and the highest 100-year global warming potential with the GWP 100 of 14,700 of the HFCs.
Yes. So as I said, I looked into the production of the refrigerants. It's a bit tricky because it's very hard to come by, because a lot also of the gases are not produced here. So generally, yes, there are emissions associated. HFC 23 usually is a byproduct of a lot of things that are heat and fluorinated carbohydrates will tend to also create HFC 23. If there are like a large amount of emissions, I can't really say, though it's true. It's the most problematic of the HFC F-gases. So this is a problem, and generally, but there are CO2 emissions attached to ammonia and CO2 and hydrocarbon production. So there are emissions attached to that. They are lower, and if you include they're quite lower, to be honest. Especially the HFOs have a larger fingerprint also than the HFCs, some of the HFCs. So it's very hard to capture that and to include it all. But generally, it seems that the fluorinated refrigerants add a bit to the a bit more to the overall emissions, including the productions compared to the naturals. Yes.
Thank you very much for clarifying. And with that, we have to say goodbye to you, David. Thank you for being present in our networking break, which will start, let's say, around from 1 hour from now, so 4:30-ish CEST time. And thank you for also being present tomorrow in session number 6, where our participants will get the possibility to engage in further discussions. Thank you, David.